Hello and welcome to this presentation. I will be talking about a new strong direct sum result for the majority function in query complexity. This is joint work with Mikaios. So as a first step, I'd like to recall a few definitions about query complexity. At the heart is a Boolean function f, taking n-bit strings and outputting either 0 or 1. One of the simplest models to compute any Boolean function is the following. You're allowed query access to the bits, and you can choose which bits to query adaptively, depending on what you've seen already. So this describes implicitly a decision tree, where each node is a variable you query, and then each internal node has two children, depending on the outcome of the query. For instance, a decision tree that computes the end function on 3-bit could look like this. It would first query x1, and if it sees a 0, then it would output 0 because the end would be 0. And if it sees a 1, it decides to query x2 up until x3, and if it has seen only 1s, then it outputs 1. So now the game is to find naturally the tree which makes the least query. And we define the deterministic tree complexity of a function f as the minimum depth of a tree, a decision tree, that solves the function f. Okay, so as usual, we may spice things up by considering randomized decision tree. So allowing our tree to make randomized decision. So a nice way to view those objects are simply to see them as a pair where you have a set of deterministic decision trees and a probability distribution on those decision trees. We say that a randomized decision tree T computes F within error epsilon, as noted here, if for any input, the probability that the tree gets the answer wrong is at most epsilon. This allows us to define the randomized epsilon query complexity of F as simply the minimum tree amongst all those that solves F to within error epsilon. And the cost of a tree is simply the worst case. So worst input and worst randomness of the tree. Worst case of randomness in the tree. Okay, so we will usually disregard constants, and we will simply note R of F for bounded error. So now the question is, how do you get lower bounds in those models? So, well, for deterministic tree, you have adversarial arguments, and for the randomized case, you have minimax theorems. So this works well for simple functions like AND, OR, XOR, majority, etc. But what if we have more complicated functions? Well, one way to build complicated function is to compose smaller ones. And so I want to talk about query composition in decision tree models. So we will have two functions, the outer function f, which takes n-bit strings, and the inner function g, which takes m-bits function strings. The composition f composed with g simply takes n times m length input and returns 0 or 1 in the natural way. So that this defines this tree-like computation. Okay, so now the question is, how does the deterministic tree complexity of f composed with g behave with respect to the deterministic tree complexity of f and the one for g? Well, the answer is easy. There is a multiplicative relationship. The upper bound, and this is exact, so the upper bound comes from the following. You just take the best tree you have for f, and every time it needs a bit of the inner copies, it just takes the best tree for g, and you get this. The lower bound comes from one of those adversarial arguments. So now you may wonder what happens in the randomized case. And well, here it's a bit more complicated. So as a warm-up, let us try to do the thing we did with deterministic decision trees. So we would take a randomized decision tree for f with bounded error 1/3. And every time it needs the answer to one of the inner copies, it calls a randomized algorithm for G with bounded error 1/3 also. Well, it's not hard to see that without assumption on F or G, there is no way to bound the error probability, right? Basically, the only tool we have at disposal is the union bound. And it's not strong enough to support what we need here. So, okay, a quick fix is simply to amplify the success probability of each of the copies. And more precisely, we need to take error probability 1/n because there are n copies. So, okay, so with this in hand, we get the following relationship. We get that the randomized query complexity of F composed with G is at most the randomized query complexity of F times the randomized complexity of G, but with our probability reduced to 1/n. So, well, is this amplification step necessary? So again, sometimes it does, sometimes it does not. It depends on the outer function f. And for now, there are no conjecture as to which outer function need it and which don't. So let me now talk a bit about the landscape of all results that are known. So we've seen the naive upper bound, right? But sometimes you can beat the naive upper bound. For instance, for the R function, you don't need to amplify the inner copies. There is a clever algorithm that somehow hedges all the errors, and we can thus save up on computation on the number of queries. So this is a folklore result that emerged with the study of noisy decision trees. So for general lower bounds, we have two recent papers. This one from Ben David and Kotari, which introduced sabotage complexity, and this more recent one by Ben David and Blais that introduced this noisy query complexity measure. So, okay, we haven't answered our question yet. So are there functions that need amplification? Well, it is established that the identity function on n copies need the error reduction. So basically computing n copies in parallel takes n times the cost of computing one copy, which is quite natural. This kind of result is called a direct sum result. So there is a bar over this R. It's because we're taking expected cost. That is, instead of worst case over all worst input and all randomness for the tree, we take the average over all the randomness of the tree. You can just disregard that or just simply think of example of function where those two measures are actually equal, the average case and the worst case. There exists some function. We will actually see one. Then last year, this was proved also for the outer function XOR. So this is a result by Brody and al. And yet, so they proved it for XOR. And our new result is that this strong direct sum result also holds when the outer function is the majority function. Okay, so let me talk a bit about it now. So, okay, we want to say that the majority function needs amplification. So our theorem is the following. The randomized query complexity of majority composed with G is at least n times the randomized average case randomized query complexity of G with error amplified, so to 1/n. So we have n instead of randomized query complexity of majority because those are equal. Actually, you can use a minimax theorem to prove that the randomized query complexity of majority is at least omega of n. So the proof strategy is as follows. We suppose toward contradiction that the above relationship is not true. That is, there exists a randomized decision tree T, which computes f, so any function f composed with gn. So later we will derive a contradiction when f is the majority function. So okay, we take such a tree, we assume it has error 1/3, and also has a cost which is too good to be true. So little o of n times the average randomized query complexity of G with error probability 1/n. Now, given this too good to be true tree T, we extract a new randomized decision tree T prime, which solves F composed with gap OR instead of G. So gap OR is simply the OR function, but with the premise that the input is either the all zero input, or it has exactly m/2 ones and m/2 zeros. So that's gap OR m. So this is strictly simpler to solve than the OR function. And actually we have that the average case randomized query complexity of gap OR where the error probability allowed is epsilon, is exactly theta of log 1/epsilon. So the lower bound, the upper bound comes from the algorithm that samples log 1/epsilon location and answer 1 if it has seen a 1 and 0 else. Okay, and this is one of those functions which has the same average as worst case warranty. Great. So yeah, so given this too good to be true randomized decision tree for F composed with G, we extract one for F composed with gap OR, and now we use a result of Ben David and et al., which says that whenever F is the majority function, then actually composing majority with gap OR is hard. So that there exists no such shallow or randomized decision tree. So to be fair, we're not quite able to extract a randomized decision tree, but rather a conical junta. So this is a generalization of randomized decision trees, and you can see them as randomized decision trees where leaves have some weights and some can overlap also. So, okay, it's a generalization, but the result of Ben David et al. Is strong enough to handle that case. Okay, so rather than dwelling on this reduction, I'd like to bring your attention to the fact that we're actually doing something quite interesting. So we're transforming any instance of F composed with G into an instance of F composed with gap OR. So how can we do that? Well, I'm gonna now explain what's so special about gap OR and how to put any function under the same footing as gap OR. So first, we need one slide of definition, and this will be about leaves of deterministic decision trees. So suppose you have a decision tree T, so maybe it looks at x1 first, and if it's 0, it looks at x4, and if it's 1, it ends up at leaf L2. So one thing that we can see directly is that leaves are partitioning the input space. And as such, we can see leaves as indicator function that are actually filtering inputs. So for instance, L2 can be seen as the polynomials, which is 1 minus x1, because to arrive to L2, you need x1 to be 0, and then multiplied with x4, because you need x4 to be 1. In the same vein, you would have L4 equals x1 times x8. So this formulation is quite nice because we have that if an input x ends at a leaf L in your decision tree, that's if and only if L of x is 1. Okay, so a nice trick with this is a characterization of the output of the tree. So an input x, T outputs what? It outputs basically the sum of all the indicator leaves for any leaf which is accepting. So we say that a leaf is accepting if it outputs 1 and non-accepting if it outputs 0. So this is basically the idea behind the transformation. Okay, so as a last nugget of definition, we will let L of mu for a distribution mu simply be the probability that the leaf L is reached when the input X is drawn from mu, or equivalently the probability that L accepts an input from mu. So mu is a distribution over bit strings of size n, for instance, the domain of G. Okay, with that under our belt, we can now explain what's so special about gap OR. So suppose that you have a tree T, so deterministic tree T, that solves gap OR. So maybe it looks at x42 as its first query, etc. And suppose further that the depth of T is small. In particular, it makes at most little o of the average randomized query complexity of gap OR when the error allowed is epsilon. So we've seen in a previous slide that this is theta of log 1 over epsilon. Okay, so you have this tree that computes gap OR m, and it's shallow. And now you let mu0 be a distribution over no inputs of gap OR. So we don't have much choice because there is only one no input for gap OR. It's the all zero vector. And we will let mu1 be a distribution over yes inputs for gap OR. And here we're taking a uniform yes input. That is an input which has exactly m over 2 ones. Now the observation is the following. So if under mu0 you can end up at a leaf L, then there is also a small probability that you end up at L with distribution mu1. So that in a sense, L is one-sided noisy. Whenever you reach some L like this, you're never sure if it came from mu0 or mu1. And the claim is that any shallow leaf has this property with respect to mu0 and mu1. So let's quickly check this fact. Okay, so we will break this in two cases. So as a first case, we take a leaf which has somehow a positive literal. So recall that the leaf is simply a conjunction of literal. So now let us think that there is at least one positive literal. So maybe the leaf is looking at x42 and asking it to be 1. Well, it's easy. Such a leaf, you would have probability 0 of arriving at that leaf if you came from mu0, right? Because mu0 has only zeros in its input. Whereas you would have some small chance of arriving at it with mu1. So in that case, the lemma holds. Now let us discuss the more interesting case where L has some positive literal, has no positive literal. So L would look like this. So maybe it asks that x1 is 0, xm is 0, maybe it also looks at x8 and asks it to be 0, and then it doesn't care about the other things. It's not checking because it's a shallow leaf, right? So there are exactly L location for which L is looking for a 0. So, okay, first thing to notice is that an input from mu0 has a 100% chance of landing at L, right? Because it's the all zero input, and this leaf L is looking for only zeros. But now notice that an input from mu1 could still fool L, right? This is because L is supposed to be shallow. So the length of L is at most log of 1 over epsilon, and an input from mu1 actually has m over 2 zeros. So the probability that an input from mu1 fools L and that L accepts is at least epsilon. And so we have our result. So basically, we've shown that any shallow leaf of a tree that computes gap OR has one-sided noise. And now comes the crux of our results. It simply says that this is true for any function g you want to choose. So more precisely, for any function g, you can find a pair of distribution mu0 on no inputs of g, and a distribution mu1 on yes input of g, and the hard side b, either 0 or 1, such that whenever you encounter a conjunction which is too small, then you have that it has some one-sided error. That is, if there is some probability to reach it from the hard side, then there is also some probability to reach it from the easy side, or say the non-hard side. Okay. So a few remarks about this lemma. So first of all, the hard side B is important, right? We've seen with gap OR that the hard side B is 0, and it couldn't be 1, because any leaf that is looking for a positive literal would have literally 0 chance of coming from mu0, whereas it would have some chance of coming from mu1. At the crux of our result is a minimax statement that witnesses the hardness of average case randomized query complexity for G. So for technical reasons, this goes through trees that can abort. And yeah, this is due to Blaise and Brody. Okay. And as a final detail, we actually need something stronger than the results, in the sense that it needs to work for almost all leaves and not on an average run over the tree. Okay, so now that we have we understand somewhat more the result, let me talk about a few open problems that we have. So I mentioned briefly those conical junta, this exotical model. So recall that we had a randomized decision tree T, which was too good to be true and was solving the composition of F and G with too few queries. And from this, we were to extract a conical junta. So this is, even though it works, it's kind of unsatisfying, and we wonder if it's possible to extract a classical randomized decision tree. So that would be an interesting question. Another question is to prove more of those strong direct sum results. So for instance, our proof structure can also handle the XOR results of Brody et al. Although it is much more complicated than the original proof, but we also think that it could handle easier outside function like gap majority. So gap majority is simply the majority function with the premise that yes and no inputs are well separated. In particular, that the Hamming distance has a square root separation between those two. So we think that our machinery could also perhaps show a strong direct sum result for gap majority. And lastly, so this is a bit more technical, but the hard side B is important in the reduction also. So whenever B is 0, we need this conical junta lower bound for F composed with gap OR. But whenever B is 1, we need this reduction for F composed with the negation of gap OR. So this is fine because for majority, we can extend the result of Ben David et al. For the negation of gap OR. But in the general case, we're curious if there is actually any difference at all. So we're looking for a function f, a Boolean function f, such that the randomized query complexity of f composed with gap OR would somehow be larger than the randomized query complexity of f composed with the negation of gap OR. So that would also be an interesting open question. Okay, so thanks for your attention.